Hello and welcome to the Queermonge Institute, our Q&A Conversation for Exploration series. I'm Paul Robert, the Executive Director and President of the Institute, and along with my wife, Laura Lee, the Director of Research, Education, and Outreach. And of course, on behalf of our Board of Directors, advisors, volunteers, and supporting members, we want to thank you for joining us today. The Queermonge Institute is an independent, nonprofit research organization committed to researching consciousness and the human experience following the footsteps of our founder, anthropologist Dr. Felicitas Goodman. And as an educational institution, we take an open approach and invite scholars in related fields to help broaden the scope of our own work and exploration. That's why we call this Conversation for Exploration. On these weekly Sunday discussions, we've had a full spectrum of topics, including neuroscience and anthropology, art history, archaeology, mythology, archaeoastronomy, and much, much more. And you're welcome to visit our website at queermongeinstitute.com. All of our presentations are free, and as a nonprofit, we invite you to become a supporting member. And of course, we want to thank you, the community members, who continue to support the mission of the Queermonge Institute. Recently, here on this program, we've been discussing the underlying patterns of the universe from various angles and a variety of guests. And today, we continue that search and reveal more secrets of the universe using math as our guide. That's a tool of theoretical physics that our guest here uses to confirm some of these patterns. It's also mathematics that hints at the many more than 4 dimensions, if you include time, we live with on a daily basis. So let's go on a journey to further explore the unseen realms of the universe and look at the mind-bending implications of a multidimensional universe. So it's through the universal language of mathematics and with theoretical physics that we continue to explore the secrets of the universe.
Well, our guest today is works at the Max-Planck Institute of Gravitational Physics. And before we introduce our guest, I just have to say, imagine working at a place where the founder, who is the father of quantum physics, where the founder is both scientist and mystic, I would say, because here are some of the things that Max Planck himself said. He said, "I regard consciousness as fundamental. I regard matter as derivative from consciousness. We cannot get behind consciousness. Everything that we talk about, everything that we regard as existing, postulates consciousness." And who says, "All matter originates and exists by virtue of a force which brings together the particle of an atom to vibration and holds this most minute solar system of the atom together." So looking deeply at those secrets of the universe, imagine working at an institute where this is the quest, and where they say, when you change the way you look at things, the things you look at change. And science cannot solve the ultimate mystery of nature, and that is because, in the last analysis, we ourselves are a part of the mystery that we're trying to solve. And, let me just continue. What seems today inconceivable will appear one day from a higher standpoint, quite simple and harmonious. And that's the quest, right? The unified field theory, to understand nature's secrets, to understand ourselves through understanding, as Newton did long ago, God's handiwork. That's the quest. So we're going to find out who Max Planck is, but also Shane Farnsworth, our guest, is going to tell us about his work there, his day job, using math to look at both patterns of nature. We spent a long time looking for those patterns, underlying patterns that would reveal the secrets of the universe and ourselves. But he also says the math hints at, shows, gets a glimpse of more than our 4 dimensions that we know. 26 dimensions, 11 dimensions. Why is that? What would those look like? How do they work? Where are they? Why are we only seeing a few? Is that this in limit of our own sensory apparatus? Do we have to grow in consciousness to be able to comprehend the others? Where are they hidden? Is it nested Is it vibrational? Can you have many dimensions in one space depending on the frequency? So many great questions about this. And these are just a few, because Shane also is the host of Escaped Sapiens. And so he gets to interview scientists of all stripes, much as we do here, and go exploring. He's Australian. He lives in Germany. That's where the Max-Planck Institute for Gravitational Theory is. But what a fun day job, and this podcast that you do. Host to host, this is fun. Thank you and welcome.
Thank you so much for the invitation. Thank you for having me on your show.
Well, first of all, tell us about Max Planck, and then tell us why you're there and what your mission is with your work there. What your personal mission in life is as well.
So I prepared a couple of pictures. Should I put them up? Would that be good?
Sure.
For people who aren't familiar with
Max Planck?
Yeah,
sure.
I'll put, just so people can see who we're talking about. Can you all see this? Is this visible for you?
He's a Nobel laureate winner and Nobel Prize winner, and he was a friend of Einstein. I do know that.
So yeah, he's a very interesting guy, and if you Google him, this is the first image that will come up when you do so. And I must say, I don't really like this image of him because it makes him look severe and sort of grumpy and maybe sad. And the reason I don't like this image is because he had a fairly difficult life in some ways. He had 5 children, 4 of whom died. His oldest son, unfortunately, was killed in the First World War by the French. His second son was killed by the Gestapo in the Second World War because he tried to kill Hitler. He tried to assassinate Hitler, and he got captured and executed. And both of his daughters died in childbirth. So and his wife also passed away.
A lot to be sad about.
Yeah, so he had a very a rough time of things, and so this photo was taken when he was 75 years old or something like this, and he'd had many sad things in his life happen, and there were quite a few sad years ahead of him coming. And so I don't really like this picture of him. I prefer these pictures of him. So these images look a little bit less distinct. Well, the one on the left looks a little bit less distinguished, and I'm not putting it up there to make fun of him. I find these images more
you relate
humanizing. I somehow connect to them a little bit better. But so this is when he was quite young, and one of the interesting things about him was when he was about this age, and he originally wanted to go into physics. He approached his supervisor, the man that would become his supervisor, and he told his supervisor that he was interested. And he was told not to go into physics. He was told that everything had already been discovered.
We've heard that before. Yeah.
I think it was a pretty common thing that people said around then. But yeah, they thought that they only had to wrap up a few, cross the T's and dot the I's. And he, despite what his supervisor said, he decided to go into physics anyway, and he revolutionized the field. He became the father of quantum mechanics, which is a pretty massive thing. So another thing that's interesting is originally he couldn't get a job. He was unpaid as a lecturer. So there's hope for us all in research. So he's a very interesting guy outside of the research that he did, as well as the research.
Never give up.
So I could tell you a little bit more about his research and what he did, if that's interesting for you, or would you prefer to hear about me, or what's most interesting?
Could you summarize what his discovery was that opened up this entire new field of physics?
What he's the most famous for?
With the quanta, electrical, energy quanta. What is it? What was his discovery initially that set the stage?
So he discovered something that's really astounding and really amazing and quite beautiful. And when he discovered it, he had no idea that he'd discovered it. He thought it was just what he discovered was just a mathematical trick. He didn't give it sort of the the amount of importance that it actually, he didn't realize what he'd done. And so what he did was the following. Let me paint an image of what he did. So there's this really beautiful physics fact that you probably know about, and people in the 1800s knew about when he was sort of thinking about these things, but which you probably haven't thought about in a particular way. So if you look at your hands, if you look down at your hands are glowing. Your whole body is glowing with radiation. So even though you can't see it, everyone is glowing with radiation. And the reason you can't see this radiation is because it's not in the visible spectrum. It's outside of the range that your eyes can see. If you want to see this glowing radiation, you have to heat the object up that you're looking at. So you're very familiar with this, right? So you can see this radiation with a special camera, right? So you can see it with a thermal camera. So a thermal camera is very different to a regular camera. With a regular camera, light comes down from the sun or some light source and it bounces off you and hits the camera. So you're seeing reflected light.
Okay.
You might not have thought about this, but a thermal camera is very different. If you look at this thermal image that I have on the screen, that light isn't coming, it's not reflected light, it's coming from their bodies itself. It's light that they're glowing with this thermal radiation. Right? So it's very different and quite special. And if you want to see this radiation, if you want to be able to see it with your naked eye, then what you need to do is you need to heat an object up. So all objects do this. Very cold objects have not so intense light and it's outside of the frequency that you can see. But if you look at the coals in a fire or a heated up metal bar, you'll see that they glow, right? So every object in the universe glows with radiation. It's just the intensity that changes and the frequency that changes. And so why am I telling you this? The reason why I'm telling you this is because people knew about this in the 18th century. And they wanted to explain it mathematically. They wanted to have equations to describe why objects glowed like this. And when I say like this is what I mean. If you look at this image that I have on the screen, this object is not just glowing, one color, but the region of the object that's hottest is glowing white. Then when it cools down a little bit, it glows yellow. Then a little bit cooler, it glows red. Then a little bit cooler, it'll glow outside of the range that your eyes can see. So you can look at this metal bar on the screen and you can see there's a region doesn't seem like it's glowing. It really is. Mm-hmm. But if you touch that bar, you'd burn yourself, right? So it's just glowing outside of where you can see, right? And if you go down cooler, you get to sort of us. We glow like way outside of where you can see, right? Okay, so this is a simple bit of physics you're probably familiar with. You may not have thought about too deeply, but people wanted to explain why objects glowed the way they did. Now, and the sun, of course, also is bright white hot because it's at about 6,000 degrees. That's why you see it as being white. So anyway, so people knew about this and they tried to plot. So here's a plot on the screen. It doesn't really matter. You don't need to worry about it. It might look complicated, but you don't need to worry about the details too much. All you need to know is that people, they looked at objects of different temperatures and they plotted what the light looked like coming from those objects. And they didn't know, they wanted to calculate, they wanted to use first principles and calculate these plots, and they couldn't do it. So they tried for many years to reproduce mathematically these plots, and they always failed. And Max Planck tried for 7 years. He tried for 7 years to reproduce this plot mathematically. And so these three colored plots, the blue one, the green one, and the red one, is what the plot should look like. Don't worry too much about what they look like. That's just what they should be. Mm-hmm. And the black one is what he got from his calculations. Completely off, completely wrong. And what his plot indicated was that all of us should be frozen to death. Okay. If his plot was correct, we'd all be completely frozen to death. No one would be able to live. And so it was a big problem. And he, as I said, he worked for 7 years, right, on this problem. And here's the big thing. Here's the reason why I'm telling you this.
Because he had to think outside the box.
He had to think outside the box. And what he did was the following. Most people thought when matter glows, it can glow at any frequency at once. That's what classical physics would say. But Planck, after 7 years of trying and getting the wrong answer, he said, what if I just let light be, it can't have any frequency, but it has to have very specific frequencies. It comes in little packets of energy that I'm going to call quanta.
Okay.
So he did that, and he took that assumption, he put it into his equations, and bam, he got exactly the curves that nature gives. And so that was the start. That's the start of how quantum mechanics came in. It just assuming, rather than that light can take any frequency at once, it takes very specific quantized bits of energy, little packets. And so that was the beginning. And the thing was that he had no idea. He thought it was just a mathematical trick. He didn't realize he'd just created a whole new field of research. He thought it was just something that would be, explained away as a mathematical trick, and that we'd work out a better way of doing things down the line. But it turned out not to be true. It turned out that he'd really discovered something quite remarkable.
And it shows how math was the instrument by which you reveal a whole new set of laws of physics, much as you're going to look at today, extra dimensions, patterns in the universe. So this math is a very useful tool. Yeah.
Sure.
Yes.
So
How did you get involved in all this?
Yes.
how did I get involved in all this?
What was the lure for you? Yeah.
What was the lure for me? I'm a mathematical physicist, and what I'm interested in is there's a very particular question that makes me really curious, and it might seem like a very simple question, but I want to understand. So there are lots of different particles that we see in experiments, and there are different forces that we see. And I want to understand why it is that we see the particular particles that we see, and why we see the particular forces that we see. Because so if you think about things, if you go back about 100 years ago to the 1930s, things were very simple. We had protons, electrons, and neutrons that made up everything. Those are the three particles we knew about that made up all of matter. And we had electromagnetism, light, and we had gravity. That was it. So the story was very simple. But now, after 100 years of research, we know that the proton and neutron are not fundamental. They're actually made up of smaller particles. That it goes down even further. And if you do all the counting, we've discovered about 100 different types of fundamental particles.
Oh,
so there's now neutrinos, there's quarks, there's
bosons.
There's the bosons, there's the particles, antiparticles. So there's this whole, and we've also got the Higgs field. So there's this whole soup of, this whole set of particles. And the question is why? We've also got new forces. We've got the weak and strong nuclear forces in addition to electromagnetism. So I want to know why, because it's very pretty, but it's rather baroque. If you were going to guess, if you were going to imagine a universe, you probably wouldn't imagine it with the particular 100 particles that we do have with all their weird properties. So that's sort of what drives me on the physics side. And then there's what drives me on the science communication side. So that's what I want to find out. But there's also another big question, which is how to get these stories out to people. Because you've probably noticed that, so people in the audience are probably familiar with watching all the brilliant science documentaries, and of course, there's brilliant science journalism. But one problem with the journalism that you might see is it's really sanitized, right? You often see the amazing discoveries. You see at the end of the line, after people have put, as I said, Max Planck worked for 7 years on uncovering this.
The sweat and uncertainty, the politicking, the questioning. Do we really have all the fundamental bricks to lay this foundation? Is this a house of cards? Mm-hmm. All of that behind the scenes, yeah. Exactly.
So, and you didn't see that he was unemployed. Well, he didn't have a paid job. So all this sweat, and At the moment in our
The
society,
human
there's
story.
the human story. And I find that story really interesting. And there's also in our society at the moment, this anti-science sentiment in certain areas. And I feel like if people could really see what scientists do and see that they're people and what they, see the failures, see all the different pieces. One way of understanding what I do is that, so one thing is to understand what geometry is good for. So I think I explained this to you before, Laura, but like imagine if I wanted to tell you about some shape that I was very much interested in. I wouldn't have to tell you about all the side lengths and angles. I can just tell you about some subset of those things, and then you can use the rules of the geometry to fill in the missing information.
Gotcha.
Right? So the idea is that if you have a geometric description of nature, if you have a geometric description of particle theory, you can think of the details of that theory sort of like the side lengths and angles. And so if you know certain information about certain particles, and you might be able to predict using your geometric rules that there's some particle we haven't seen yet in an experiment, or you might be able to find that, hey, look, there's that particle that appears at this mass and with this charge, and it does so because it has to fit these geometric properties. So that's the basic idea.
So you can't really look at what you're looking at under a microscope. You're really looking at the implications of its behavior, the physics that the equations of that. You're really trying to deduce. It's like a detective story. You really can't see the object of your quest, but you can see the wind through the heads of wheat, right? You can see its tracks through nature, in a sense. So this is, and then you're looking for patterns to say, well, of all the possibilities, if I see consistent patterns, that must be the path I should take. It's like following breadcrumbs through the forest. Is that rather what it feels like?
Yeah, they're hints. I should say that at the end of the day, experiment is always king. So no matter how good your hunches are and your hints are, at the end of the day, experiment is always king.
To confirm it, yeah.
Absolutely. And I have a funny anecdote, actually. There's a funny story that I could tell about. So patterns are wonderful in some ways, but also they can cause you to go down a wrong path sometimes. So there are very good examples of cases where people have followed patterns that have been completely wrong, and in hindsight it looks silly. And then there are other cases where we've discovered particles, we've uncovered brilliant new things just by following our nose and following the patterns that seem to occur in our equation. So can I give you an anecdote about this sort of thing?
Please,
so I've got another, I prepared another, I prepared a lot of images. I don't know which one's going to be useful in the conversation, but I have a lot of images. So I'm going to mispronounce these guys. I've never heard anyone say their name, so I'm just reading it. So if I butcher their names, I apologize, but I'm going to call them Titius and Bode. These are two chaps from the 1700s. And back in the 1700s, people were very interested in the planets. Right? They were looking up at the solar system, and they were seeing things like, the planets had different orbits, and they had different sizes and all different properties. And they were trying to explain the different properties in the orbits. And they noticed something really peculiar. So they noticed if you look at the distance between, so the planets go Mercury, Venus, Earth, Mars. If you look at the distance between the first two planets, it's roughly half the distance between the next two. And then the gap from the first two, if you go from the first gap to the second gap to the third gap to the fourth gap, between planets 1, 2, 2, 3, 3, 4, it always doubles, right? They noticed this funny thing, that these gaps were doubling. And so they predicted that there's this fundamental law of nature that the distance between orbiting bodies always doubles with each.
Further from the sun. Okay.
Exactly. Yeah. So there's this funny quote here. I'm not going to say the quote because it will take some time. But the point is that today we know this is completely false. right? We know, they had this wonderful mathematical law, and not only did they have this law, but they made predictions that turned out to be correct, right? They predicted the position of Uranus. I think it was Uranus, and that turned out to be correct. And then they found some asteroids that were further out, and eventually, I think it was Neptune didn't fit the pattern. And of course, today we know that if you look at the orbiting moons around Jupiter, we know they don't fit this pattern. And we know there are different solar system, there are other stars with planets orbiting that don't necessarily satisfy this rule. So we know that this was just sort of cosmic chance. That we know that it's sort of, you shouldn't be looking for a fundamental reason why or a planet's orbit.
And beware your pet theories, because it sounds nice. It makes the universe feel very ordered, but it turned out to be a pet theory that was hard for them to let go. I'm suspect. Yeah.
And they had a mathematic, they had an equation. So my point is that sometimes it's not always clear that the questions you're asking are good, right? On the other hand, we've discovered, as I said, particles by looking at patterns, and we've discovered all sorts of amazing things. So I just thought, before we jump into things that are speculative, like why the universe has certain dimensions and something, I thought I'd put that warning out there.
Right. That's why I say glimpse and hint, but nothing's proven in all of this. Yeah. But you have to go down those wild paths, right? Because plate tectonics is a good example. It just seems so absurd at the face of it, and yet some of those absurd things turn out to be true.
I can see Bert Webb has his hand up. I don't know if he wants to ask a question.
Go ahead, Bert.
Great last name, by the way. I'm wondering if it's related to James Webb.
I don't believe so, but it is kind of interesting in light of the launch of the telescope. I just wanted to point out that there's a psychological process that's called apophenia. And what that means is you see a pattern where there isn't one, like you see a rabbit in the clouds and so on.
Okay.
And specifically, there's a
Piece of Jesus in a potato chip. Yeah.
Exactly, or a cheese grilled sandwich. I always like that one. But there's a one that's limited more to the visual. It's called Pareidolia. It's the same. That's seeing the rabbit in the clouds and so on. And apophenia is a more general term. But it seems to me that Bode and Kepler and his Platonic solids between the orbits of the planets, the idea is the pattern is pretty, the idea is attractive, and yet it's not true, or it's not completely true. There's some issue or problem with it. I always make it a personal practice to be very careful about believing in something I want to believe in. And of course, if you're heavily invested in a field of science, and you got a pet theory, boy, do you want to believe it's true. I had a short anecdote. I was a programmer for a long time, and programmers hate bugs. They just really do. And then they sent me over to testing, and it turned out that testers love bugs because that's what they're supposed to be doing. So it's, and I always like the definition of the word cynic is somebody who believes that human institutions may be perfected, but they're not perfected yet. So anyway, all of those things add up to reinforcing what Shane is saying, is that are the patterns really there? I mean, our brains are programmed to continuously look for patterns. And there's a thing we tend to have more false positives. For instance, if a lion is creeping through the bush to attack you and you see the plants moving, it's better to think that's a lion, even if it's the wind, and get out of there, because if you're wrong, you're dead. Right, that you're safe. So we process patterns, we live by patterns, they're all around us, it's where our brains work, but we have to be careful to walk that tightrope of what is and what isn't, and how we're determining that.
But of course, on the other hand, occasionally the patterns lead you to a tiger, right? And
that's the point. It's better to be a little bit more paranoid about these things and to err on the side of it is a tiger than that it's not a tiger. If you just work out the matrix of possibilities, it works out. If you maybe are shaded a little toward the paranoid.
Well, I think that's where the part of our brain that can respond quickly without going through the intellect to analyze it saves us. see pattern, respond,
Yes.
get yourself out of the way, even if it's the wind. So we're programmed for that. That's a good point. We have to look at our own biological imperatives and navigate around them on the search for truth.
And in terms
So-
of searching for, a reality that you can't see or directly, when they were trying to figure out the nucleus of an atom, they were firing particles at this atomic nucleus. What they were reading was the scatter pattern. So in other words, they got a silhouette. Nothing went through where the nucleus was. Everywhere else, you saw particles hitting the screen. So it's kind of like what's not there, right? Can sometimes lead us to what we're looking for.
Yeah, thank you for that. Do you want to speak to pet theories a little bit and the danger of that?
Oh, yeah. I mean, well, there's a few different. There's a danger. Do you mean the danger inside research or outside research? Because often when you're listening to here's a danger that is more relevant to the people perhaps in the room when they're watching someone talk about physics. So when you're watching that documentary or you're watching
Right, thank you.
someone talk about things, often people like to talk about their own pet theories. And if you're not involved in that particular theory, you can't tell how well accepted this theory is. And so that's one of the dangers of pet theory. So I'll tell you a little bit about what I work on at the moment, but I'll be sure to tell you that it's not necessarily the most widely accepted theory. But
those are the ones we like.
Right. Well, it's accepted by some, but
Well, we could apply it to the dimensions, right? It would be really easy to explain a lot of phenomenon that has no explanation by saying, well, there's more to this universe than we can detect through our limited bandwidth of our technology, our own sensory apparatus. We've done a big job putting the telescopes up in space to see wider. We've seen with the microscopes, we can see deeper. With the particle accelerators, we can start to tease out those particles that make up the atoms and make up us. But what does it all mean? I mean, we can make huge leaps of implications, which I'm very fond of doing. And I say, I can speak in a mythopoetic language. I don't need to be accurate. It's a good analogy for me. But the danger is, where do you separate out something that's a good analogy from actual reality, right? Because we tend to speak in a language that's very imprecise, and where we want to make leaps and metaphors, right? It's the reason I was an English lit major. That was easy, right? It gives me a lot of license. But then, how do you really understand what it's all about here? I've concluded, let the mysteries be the mysteries, right? I'm not the cynic. I don't know that we'll ever understand it all, and I'm okay with that. Be comfortable with the unknowns. That's another stance that makes life much, much easier.
If I have 500 degrees of freedom, I can explain anything. Yeah.
Yeah.
The Bob would work.
Bob, yeah. So
I can't see you, Bob. Sorry. Oh, Woodruff. I know this name, Bob Woodruff, from somewhere. Why do I know this name? Were you in the previous discussion I had with Laura last time, or?
Oh, Bob, would you like to introduce yourself? Talk about the Hubble.
Yeah, and my camera's not working. Yeah, I'm an optical designer. I've been designing space telescope spectrometers for 55 years. I really involved in the design of Hubble. I designed most of the instruments on Hubble. I was in the middle of analyzing the spherical aberration problem.
Okay.
I did the first design on James Webb. I designed Kepler. I've got a lot of things. I'm an optical physicist.
Mm-hmm.
He's somebody you want on your podcast, Shane.
Yeah, well, this is why I've heard of the name, because you're out of field for me. But it means you must have done some good stuff if I know your name, and I'm out of field.
Help design the James Webb as well.
I've had a lot of opportunities, yeah, and I'd love to talk to you about photons. I'm trying to determine how big is a photon. So anyway, yeah. Anyway,
well, that's something that might turn up in this discussion. But so should I sort of explain maybe what would be interesting? I don't know what's interesting to people, but I can sort of give a bit of a cartoon of where these ideas of higher dimensions come from. if
Thank you,
that's
Yes,
interesting.
let's get to higher dimensions. Yeah, thank you, Bert and Bob. Yeah.
Yeah.
How does the math, why 26 dimensions? Why 11 dimensions? Where are they? Let's understand them.
Yeah.
How do they work? What could they possibly be? It's like a fish in the ocean,
We'll give you some
right?
time
It's
to
hard to
unfold
understand.
this. Let him
Yeah.
build that whole thing
Yeah.
because this is the biggest part of the discussion.
Yeah.
Yeah.
So I should give a bit of a disclaimer that so I'm going to be talking a little bit about string theory, but I'm not a string theorist. So the
Okay.
image that I give, because this is where these numbers mainly come out. I'm not a string theorist, but I can't. I'm going to try to do things without putting any equations on the screen or without talking about
Okay.
math too much. And so what I'm going to be giving is a little bit of a cartoon, but it should give you a little bit of a flavor. It should let you sort of see, where these ideas come from and what people are thinking and what sort of patterns they're following. So what I'll do is I'll first of all just give a very short overview, and then you can tease apart the bits that you're interested, and we can go into the bits that you're interested more specifically. But okay, so talking about pet theories, so the very short story is the following. We have these two very good theories of nature. There's quantum mechanics, which describes small things like electrons, photons, these sorts of things very well. And we have brilliant calculations that match experiments to very high precision. So we're very confident in our understanding of certain aspects of quantum mechanics. And then on the other hand, we have general relativity. This is the language that we use to describe gravity. So, you describe big things like galaxies and planets orbiting one another. And both of these are very, they're very solid physics, that they're well accepted. The problem is that when you try to mix them together, you end up with problems. So it's very hard to create a unified theory which can describe things from the very small and possibly fast all the way up to the galactic scale. So we want a unified description of all of nature.
And macro to the microcosm. Okay.
Mm-hmm. So we want this unified description of nature which combines gravity and quantum mechanics. And unfortunately, the usual description in terms of there's a prescription for how you quantize a theory and how you go about building quantum theories. When you try to do that with gravity, you end up with infinities everywhere in your calculations and problems. And so people have been trying for a long time to work out a way to do this. And one of the approaches is called string theory. It's not, I wouldn't say it's a pet theory because a lot of people work on it, but it's an attempt to quantize gravity. And it turns out that when you try to build string theories that most resemble the world we live in, they have fermions and bosons, the both sorts of particles that we see. When you quantize the string theories that look most like our universe, they're only internally consistent at 10 dimensions. So that's where that 10 dimensions comes from. And the weird thing is usually most physical theories they're okay in all dimensions. So usually when you're talking about gravity, the same equations make sense in 4, 5, 6, 7, 8, infinity dimensions, however many dimensions you want. So usually there's no restriction on dimensions. So it's very funny that this restriction from internal mathematical consistency pops out in this attempt to quantize gravity. And so that's roughly speaking where this number comes from. And I guess Laura and Paul, you can pick apart the bits of the story that you're most interested in.
Okay, so 10 dimensions, you've also mentioned 26 dimensions. So why those numbers consistently show up in terms of the number of dimensions? How do you define a dimension? The ones we know about, right? That we live with every day. Then you get to time. The fourth dimension is generally agreed upon. What would the other dimensions even look like or be? I mean, what is the possibilities there? How do you describe it? We can't detect it. We're grappling with it. We just see a hint of it in making the maths work, but there must be some thought as to what they are, how they work, why we don't see them. Even Max Planck questioned that there's no guarantee that the laws of physics we know now will remain for the duration of this cosmos. They can evolve too. So are beings of higher consciousness, are they aware? It's like the book Flatland, written in 1884. That was playing with dimensions and what it must look like from a sphere to a line to a dot. All right, a wonderful thought exercise to the dot and the line, the romance between the dot and the line. It's fun to play with this and to try to understand what it must look like going down or going up in dimensions. So what is the conversation? What do you and your colleagues talk about at these conferences and, in the hallways? Yeah. How are you describing them? Give us a sense of what they possibly could be.
So this is actually a really deep question. I just saw someone's asking sort of the same thing on the chat. But this question of what is a dimension and how you determine it, and also where this 26 comes from, both are very good questions. I'll answer the 26 one first, then I'll come back to what is a dimension, because that's a little bit more involved.
Okay.
But so where the 26 comes from is the same place that the 10 comes from. So when you build a string theory, you have to determine what sort of particles I want in it. And when you look out in experiments, there are particles that we call bosons. They're like force-carrying particles. So the photon is a boson. There's also, you might have heard of the Higgs field that was discovered in 2012. That's the field that gives everything mass. So that thing's also a boson. The graviton that mediates gravity, that's also a boson. But then the things that your body is made out of, like electrons, the quarks, the matter particles, those are fermions.
Okay.
So it turns out that when people first built string theories, when they were first building them, the simplest string theories, they said, don't worry about fermions. Let's just build a theory that just has the bosons in it. So then they try to quantize that theory. And what happens is those theories are only internally consistent at 26 dimensions. Okay, it turns out that in a theory that just has bosons in it and no fermions, those are internally consistent only at 26 dimensions. And then people thought, oh, we also see fermions, so let's put some fermions in. And when you put fermions in, you do the same calculation, and now you get 10. So those are called superstring theories. So that's why you sometimes get, you might see 26, or you might see 10. Sometimes you'll see 11.
Mm-hmm.
So I won't get into the 11.
Depends on what you're putting into the equation and where it meets its sweet spot. Well, is it like 3D chess? Are you just adding layers and then you've got relations between them, and then you can, levels? I mean, give us a model of how these are all stacked or fit, or, I mean, as kids, we were discussing, gosh, how many dimensions are here? But we're living on this frequency. Like now we have fiber optics. You can have many lines packed into one. So how many dimensions are right here that we're only seeing because we're on this frequency? Something else is on a different. How does it work?
Mm-hmm. So yeah, when people talk about when people talk about dimension, they can mean many different things. They can be talking about the number of parameters in a theory, but here, people are really talking about space-time dimensions. So in a 10-dimensional theory, what they're really talking about is there are 9 spatial dimensions and 1 time-like direction, and so those extra dimensions, in the usual way that people think of them, are really exactly the same sort of thing as what we see in the 4-dimensional world. And then you might ask the question, well, I look out the window and I see 3 dimensions, or maybe 3 plus 1. So where are these extra dimensions? And I'll get into that in a second.
Okay.
But just to answer your question, just to get back to your question. So you asked, what is a dimension? And I can't see the chat at the moment, but someone in the chat also asked a similar question. What is a dimension, and what do we mean by this?
Yeah.
So this is actually something that it's a very deep question. And the reason why is because physics behaves slightly differently in different dimensions. So I'll give you some examples. So let's say, for example, I got a metal sheet, and I stretched, I've got a stretched metal sheet, a gong, and I hit that gong and it releases some sound vibrations. Those sound vibrations will be very different to if I have a ball or something and I hit that. The vibrations depend very much on the geometry of the object you're hitting.
Makes sense. Yeah.
So you can call this sort of like the spectrum of the object in some sense. Now it turns out that in 2 dimensions, 3 dimensions, 4 dimensions, 5 dimensions, all of these different spaces of different dimensions, in a certain sense, I'm not going to get into, have a different sort of spectrum. So for the people who are a little bit more mathy in the room, you have an object called a Dirac operator, and you can look at the spectrum of that Dirac operator, and that will depend on the dimension. But for the non-mathy people in the room, just think of it as like hitting a bell or hitting a sheet. They have different vibrations. So there's that way of thinking of dimensions. The other way is just what you think of when you look outside, the intuitive picture of what a dimension is, right? You can walk in that X direction, or you can walk in that Y, or you can climb in that Z. So there's the intuitive picture, but there's also other ways of thinking about it. So if I release a gas into a room, that gas will expand out depending on what dimension you're in. They'll expand out at different rates, right? If you were in a different dimension. So the question of what is a dimension is actually very very deep. There's all the way from this intuitive way to more mathematical ways. And what happens is all of these different ways of measuring dimensions sort of coincide in the string theories that people are talking about. They're really talking about regular geometries that you're familiar with. There are more general notions of geometry where the different ideas of what a dimension is no longer coincide. And we can talk about that. That's sort of like more in the direction of my research. But no, when people are talking about these 10 and 26 dimensions, they're thinking exactly the sort of dimensions that you're looking out the window at. And so, yeah, the question is then, I guess, why don't you see them?
Well, and could time have more than just the one dimension? I mean, I've read certain articles where time can work backward. Time can flow in multiple directions. Time can be eternal. Time can be sequential. So is that a possibility as well? And
The wormhole thing.
yeah, and so, kind of, does the universe create purposefully, or does the universe create randomly? Is it one universe? Is it many universes? Many cosmos? I mean, why create it if you're not going to use it? That seems to be a law of nature, right? At least for biological life.
You're asking the big questions.
Right? So, and then where are we in the totem pole? If we're only, aware of these 4 dimensions, are there beings that are aware of all of them, that are living on that level? How does it, what do you guys talk about, amongst yourselves about all this? When you're familiar with all this, what are the implications that actually start to gel out? Yeah.
Okay, so there's a few questions there. So if I forget some of them, you'll
sure,
have to remind me.
I'll remind you. No worries. I'm sure the chat and anybody wants to jump in. Yeah. So. And why is it more sci-fi playing with this, right? This is such rich turf for some sci-fi film. But go ahead.
Give him the time.
I think they are. That you can find this in sci-fi. But the first question you asked about was, and again, I'm going to forget all the following ones, so you have to remind me. But okay, so the first question you asked is, why not 2 directions of time, or why not n directions of time? And the problem is, usually if you have more than one time-length direction, you end up with causality problems. So, you could go back and shoot your grandfather, you end up with these closed time-like curves, and these are usually problematic physically. They're not really realistic. I mean, there are ways
they're
to
fun
do it.
for sci-fi, but yeah.
Yeah, there's people like Isaac Bars and physicists like this who talk about 2-time physics and things like this. But generally speaking, it's difficult to create realistic models that have more than one time-like direction.
Okay.
Yeah, is the short answer.
All right. And then why create it? Why would the universe create it if it's not utilized by something? And consciousness, right? Let's get back to Max Planck. Consciousness is the fundamental matrix of all of this. So where is that? Is consciousness more evolved do you need to be at a higher level of consciousness to really see and taste and feel and inhabit these other dimensions?
Yeah.
Where is consciousness in all of this?
Okay, so I might give an answer that might be either satisfying or unsatisfying, depending on where you where you sit on the fence. But so we should at some point talk about how you get from the 10 dimensions down to the 4 dimensions, because that will make this picture make more sense. But
okay,
it could be, just to answer your question about why is it all there if it's not being used. So it could be, in the example I gave about these planets, right, that are sitting at certain distances away from the sun, that these two physicists or scientists believe should fit some pattern. It could be that humans can only exist on a planet, that has a very particular configuration, right? It could be that in any solar system that doesn't fit this pattern, maybe too many meteorites hit the planets that could otherwise sustain life, right? So this is the sort of the unsatisfactory picture that some people nevertheless draw. So there are string theorists who believe that you start with this big 10-dimensional world. That's the fundamental structure. And through some complicated mechanisms that we can talk about, different parts of the universe, different parts of our reality take on different characters. And it just so happens, some people actually run these arguments, it just so happens that we live in a part of the universe which can sustain conscious life, which can ask these questions. And so it might be, one way of looking at this is that maybe the universe is just incredibly wasteful. So, you could have this, there's this,
scatter a ton of seeds and see which ones land on fertile ground, right? There's
in a way,
waste built into the strategy.
Yeah, like so it could be the case that you have this fundamental theory that can collapse down into some low energy theory that we, effective theory that we, this effective description of nature that we live in. And this can happen in so many different ways that you need to have an enormous universe to find the solutions that would give you the consciousness that you're interested. So that's
giant
one
lab
way.
with a lot of experiments going on in every corner, and some of them work and some of them fail. Yeah.
I personally don't really like this picture. This is not the line that I like to go down. I would like to have some, I would like to, at the end of the day, be able to derive the world that we're in and not rely on this sort of cosmic chance. But so that's one answer to the question that particularly people in the string theory side of things do they sort of juggle sometimes.
Why do they call it string theory? Where did that name come from?
Okay, so I can tell you where that came from. It depends on the level of I'll give it at a certain level, and if you want to go deeper, we can go deeper. But so I've got some more images here that actually might be useful. So I'll share my screen again.
Yeah.
There's this funny thing about nature, and this is sort of a deep idea that people worked out in the last 100 years. So there's this. By the way, I stole all these images from I had to quickly get some images, so none of these are mine, and so don't get me in trouble with the law, because I've just nicked these offline. But anyway, so there's this interesting fact about nature, and it's the following. So if you imagine imagine a puddle, right, a body of water. Now, you might have some equations which describe this puddle of water pretty well.
Okay.
Right, on some scale, let's say on 20 meters, 100 meters. The equations that describe this body of water make sense not only at 100 meters, but you can go down further to maybe 10 meters, 1 meter, and you can keep zooming in, and the physics keeps making sense. But at some point, you start seeing atoms and molecules, and so your liquid description breaks down, right? So your description of nature only makes sense within some sort of bounds. You have to be asking questions at a certain level. Now, there's this the interesting, the deep thing is that you didn't, when you were describing the water on the 10-meter scale or the 100-meter scale, you didn't need to think about atoms at all. You could completely abstract out that sort of depth. You didn't have to think about it at all. And that's often what we do in physics. So you can imagine a situation where you're trying to calculate a ball, falling from space, or from some high point to hit the ground. One of the assumptions that people make, and this is a very good assumption, is that the ball is just a point. It's just a point particle. Like if you go to high school physics or university physics and first year physics, and you want to do these calculations, you just assume that this ball is a point, and that works very well, right? But then what you'll find is, just like when we zoomed in to look at the water and we saw at some point your description breaks down when atoms start being important, when you zoom in far enough. If you drop this ball from far enough and it picks up speed, eventually you get to a velocity where wind resistance becomes important. And so then the size of the ball becomes important, right? You shouldn't really describe it anymore as a point particle, but maybe, some more complicated object. Similarly, if you were going to describe a parachute, then, assuming that this acts like a point that'd be a bad assumption, right? Okay, so why am I telling you all this? The reason why I'm telling you about this is so I can tell you about where string theory comes from, the basic cartoon idea. So it turns out that we have this nice prescription for quantizing different theories. And it works very well. So we have this prescription for quantizing particle theories and all different sorts of things. We can look at quantize, phonons, sort of quantize sound packets in materials. So there's all different situations where you can start with a classical theory and you quantize it and everything makes sense. The problem is when you get to gravity. So gravity is just, it behaves differently to the way that other theories previously behaved. What you find when you try to quantize gravity is you get lots of infinities appearing in your equations. And this often happens when you're quantizing theories. We get infinities and there's nice mathematical ways of getting rid of them. I'm not going to get into the details. The problem with gravity is you have infinite infinities, and it's very hard to clean up infinite infinities, right? And what it's telling you is that your theory of gravity is breaking down at some point, just like our water description was breaking down when you start getting really close and atoms start being important. Our gravitational theory, when we quantize it, it's good. It's at like long distance scales and in certain regimes, but in the high energies that we want to play around with quantum gravity, the theory sort of breaks down, right? And so you have to ask yourself, what assumptions went into my theory that are not so good? Like in the case of dropping this ball, maybe you want to, if you want to account for wind resistance, maybe you want to make the ball not a point, but some, object that has some surface, some size. And so one thing you could ask is, usually when we describe particle theories and theories of gravity, particles are described as points, right? That's it. What could be more point-like than a particle? So a usual assumption that works very well for most quantum theories is to just assume that our particles are point-like. So string theory, what it does is it just throws that assumption away. So now, rather than your particles being a point, what's the next simplest thing? Rather than a point, let's just have a string. So now all our particles are strings. So we're going to look at the mathematics of strings. And these strings, they can vibrate, they can have some tension, and we can quantize this theory. So that's what string theory is. You just throw away that simple assumption.
Go from a point to a line.
Exactly. And that line is just the next simplest thing. And so that's what people do. And here's the beautiful thing. People, when they first were playing around with string theory, this isn't why they were doing it to start with. They were just playing around with string theories. They weren't trying to build a theory of quantum gravity. But when you build a string theory, the different particles correspond to different vibrations in the strings. You might have closed strings, open strings, different vibrations, different tensions. What people found, quite remarkably, is naturally when you build these string theories, you didn't ask for it. Naturally, you get a particle that looks just like a graviton. So this is the particle that would mediate gravitational interactions. So in a sense, string theory predicted gravity. Unfortunately, we already knew about gravity, but if we didn't, it would have predicted gravity. So very naturally, you get a quantum theory of gravity. The problem is the theory only makes sense in 10 dimensions. So that's that's
okay. All right. That's beginning to make sense to me. All right. That's pretty cool. Yeah. So what are the implications about this? You can finally explain gravity. You can finally put gravity, which has been very elusive, into the unified field theory at 10 dimensions. Does it give a hint as to what those dimensions are? You say they're all geometries of space-time, the continuum. Does it, I mean, okay, let me back up. So you have Newton's physics, you have Einstein's relativity, and you have quantum physics. How do you put all those together into one universe? Because the universe does exist from those infinitesimal particles in the microcosm to the astronomical galactic level at the micro level. It is one universe woven together, but how do those three physics? Is it a matter of, well, when you break down water, suddenly there's no water, there's just the atoms. There's just a single hydrogen, oxygen. How does it all fit together?
That's good.
And how close are they to putting it all into one unified field theory? I understand gravity has been a problem there for a long time.
Sorry, just so I'm sure I understand. Is the question, how do we get from these big string theories, these fundamental theories, to something that looks like what we currently have with the particles?
I guess my question, I wanted to back up and say, how does Newton's physics, Einstein's physics, and you could say Max Planck's quantum physics, how do they all fit together?
Okay, so Newton's physics is sort of subsumed. It's sort of Newton's physics it deals with objects that are traveling relatively slowly, and that are not that massive. So sort of the everyday objects, your tennis balls, your rockets and arrows, that sort of thing. And when you try to, oh yeah, I should stop my screen share, shouldn't I? Oh yeah, that's a bit better. Yeah, so Newtonian physics is good in a certain regime,
right?
But when you want to start thinking about, big objects, or when you're traveling really fast, if you're traveling close to the speed of sound, of light rather, then you start wanting. So if you're traveling fast, then you want to talk about special relativity. So special relativity sort of generalizes Newton's physics to allow for high velocities. And then general relativity, that's gravitational theories, that generalizes further. So you can look at space-times that have curvature, and there you're looking at objects traveling near big gravitational masses. Okay, so the first part of your question, to answer it, is going from Newtonian physics to general relativity, Einstein's physics. You're developing a better theory which is relevant in more situations. So it's sort of general relativity overtakes Newtonian physics. Quantum mechanics is slightly different. It's first of all, it's a different sort of revolution there. So it's a different way of thinking about how to do physics entirely. So gravity and general relativity and Newtonian physics, they're both classical. So by classical, I mean not quantum. Those are systems. So that you model physics in such a way, classically, when you model physics, what you're saying is, if I have perfect information about my system, I can predict what's going to happen in the future. So if you tell me about all the charges, all the velocities, the masses, positions, you give me all this information, and in a classical system, I can, turn the handle and predict what that system is going to look like 10 years, 20 years, 100 years, a million years from now. quantum mechanics is different. It has a very different starting point. So in quantum mechanics, you're not measuring, you don't have, your equations of motion in quantum mechanics don't tell you about the trajectory of a particle. They tell you about the trajectory of the wave function of the particle. So it tells you, so the wave function tells you about the probabilities of something happening. So you have perfect knowledge of what the probability distribution evolves like. And then you make a measurement, and if the particle has a wave function which tells you that 20% chance it's going to appear here, when you do the experiment, 20% of the time that's where the particle will be. Otherwise, it'll be somewhere else that the wave function tells you it will be.
And that's where you observe the particle and then it doesn't behave. It's because you've changed it by your observation of it. Explain that one. Or spooky effect at a distance. It gets really interesting dynamics where suddenly the presence of the observer changes the whole thing. Mm-hmm. We're back to consciousness, are we not? It gets really interesting there. Or is that a misread?
It definitely gets interesting. So consciousness is okay. So consciousness is something I don't know. So it's out of my wheelhouse a little bit. So I can't give you. All right. Also, Bert's asking another question.
Yeah. Now we're sliding over into interpretations of quantum mechanics, which is a whole nother can of snakes, right? Because you have the equations, and some physicists say, don't worry about some kind of intuitive understanding of what's going on here. Just use the equations and calculate. And other people say, no, it's important for us to have a better, deeper understanding than just the equations. So there was a conference recently of physicists where they had a dozen different interpretations of quantum mechanics, and they passed out a form. They said, vote on which one of these you like. And out of this conference of physicists, there wasn't one interpretation that even got 50%. So interpreting quantum mechanics, you get into some very strange territory that we might want to explore, which is one of those interpretations is multiple realities, the many world interpretation. Another one is following on Wheeler, a great physicist studying gravity. He eventually, at the end of his career, was talking about how the most fundamental essence of the universe in some fashion is information. So I was just I wanted to ask you where you came down on some of these interpretations.
So
what would you have voted for?
If I had to make the vote?
Yeah.
Okay, so first of all, quantum mechanics has these two different pieces, right? So the wave function evolution, that seems all fine. That doesn't seem problematic. But what the measurement means, this is usually where the breakup happens, right? This is where the love affair usually ends between.
Yes, the honeymoon's over.
Yeah. So the two that there's sort of three that I like. I don't believe in any of them necessarily. So I like many worlds. I like Copenhagen, and I like pilot waves.
So
that
be
all right, decode that.
Would that be the transactional interpretation?
So the Everett's many worlds is the one that you mentioned. So this is the one where, so the idea there is every time you make a measurement, the universe splits into all the different possibilities. So the wave function tells you that when you make a measurement, the 20% chance the particle's here, 5% chance it's here, 10% chance it's here. So the idea there is that each of those chances, each of those possibilities really corresponds to a new universe which breaks off. and so that's the one you mentioned, Webb. And then there's Copenhagen, where that's the interpretation there is that you have a wave function. And when you make a measurement, the wave function collapses down to whatever your measurement was. So that's sort of the standard interpretation. So I can tell you that those are the three that I like.
Talk
There's
about
also
herding cats, boy.
One question. The problem I had with the many world interpretation, I read DeWitt's book about the work of Everett and Wheeler back in the 60s, and I read that in the 70s, I think it was. And the problem I had, what's interesting is that was a far out theory in the 70s. Now it's got a lot of popularity, which I don't understand, because here's the big question. When each possibility splits into a separate timeline, as it were, they separate out. So you have this fanning out of possibilities as time evolves. You have more and more of these universes, if you want to put it that way. The problem I've got is, where does the energy come from to create these multiple universes? Change different versions based on which path you split, how that changed. But where does the energy? It seems to me an impossible proposition that you're generating whole universes on the basis of one electron hiccuping out by Alpha Centauri. I don't.
I think so. I don't know the answer to that question, but I assume what would happen. Deal with this is, I imagine your definition of energy would. Oh, my internet connection is unstable. Can everyone hear me properly?
Yeah, I can. We can hear you.
Froze for a moment.
Yeah. So I imagine what happens is you have some. I imagine that what would happen is your description of energy, your description of thermodynamics is just continue. It just makes sense if you look at along one of those timelines. If you look at each of the steps, like I would imagine you have to have conservation of energy within one of those timelines, not necessarily across the entire. Because that's all we know. That when we work out these, when we work out all these physical principles, we work them out within a timeline. And so I imagine the statement would be that you don't have to have conservation of energy across the full set of universes. But I actually don't know the answer. That would be my guess, but I don't know if that's the right answer.
So the other question I had is, if an acquaintance of mine here in Seattle proposed a theory of quantum mechanics, an interpretation in the 80s, I believe it was, mid 80s, late 70s, and it was called the transactional interpretation of quantum mechanics. And in an article in the International Journal of Theoretical Physics in 1982, they analyzed his interpretation. And what they said was, he's clean with the mathematics, so you can put his interpretation up there with the others. And what he basically said was, to get around the idea you can't have something that information conveyed faster than the speed of light, which is then connected, of course, to the spooky action or distance. What he said was that, and there are part of the equations contain zeros in some of this math that has basically been ignored or thrown away. And he said, okay, let's postulate that instead of trying to go across time or across space-time to get from one point to another, what you're doing is the event that spawns the quantum particles, and they go out from that event, it sends out, the event itself sends out a precursor wave. It's a virtual wave, and it doesn't have any physical impact, but it's a precursor wave that goes out. And when it reaches a possible event in the future for that particle, a wave comes back through time, and it's a retarded wave. And it's like handshaking on a computer, and they vanish, disappear, have no physical impact, but yet they determine how all of these interactions and processes work. So he said the way you get around spooky action is distance, is you're not sending a signal through space-time at a given point in space-time, but you're rather moving between the past and the future with these virtual pilot waves, which is when you mentioned pilot waves, I wondered if you had heard that. But anyway, have you heard of the transactional interpretation?
No, I haven't. It sounds like it has some similarities with the pilot wave theory, but I've never heard of it. I'm sorry.
You look it up. It actually has some interesting. And
are you playing with time then? You're saying.
In a sense, you have virtual information being conveyed back and forth that just kind of vanishes when things happen, and so it doesn't have an impact on the physical particles the way we think of it. But it's a way of reconciling the books of saying, well, how can these two events widely separated in space-time be connected in any way? Because you can't send information back and forth faster than the speed of light. So if you're two ends of the universe, how does that get conveyed? And he said, instead of going this way, you're going back and forth. You're going from into the future, into the past. So it's, like I said, he squares with the math. The physics community said it's a valid way to interpret. Books have been written about it, courses have been taught, but it's really the sad, homeless child of these interpretations, right?
It's causing our minds to stretch a little beyond the pale here. But so you're talking about spooky effect at a distance where we don't see the cause and effect, but maybe we have to invoke these extra dimensions to understand it, because you're seeing that this matrix, right? There's a matrix through which an effect here has an effect on something over here. Spooky effect at a distance. You don't see it. Are we capable of, I mean, what do we understand? 5% of how the universe works? It's so much is beyond our means of detection or understanding at this stage. So we just must assume there's a matrix there could explain cause and effect if we were to see it, right? The limitation is us and our tools. Yeah.
First of all, I will check out the transactional quantum mechanics, Bert, just to. but the
Thank you.
Yeah. So usually you want to So when Einstein was talking about spooky action at a distance, originally this language was used to sort of poo-poo quantum mechanics and point out problems that it had. So and when people talk about, we only know X percentage of the universe, usually what they're talking about is dark matter and dark energy there, and that we, physical matter that we see only makes up some small
4%, something like that.
Sorry?
Our whole universe that we have been studying and agonizing over and understanding and all this cosmic stuff, 4% apparently of reality. And the rest is dark matter, dark energy, which we really don't understand.
That's 100% correct. Whenever you see, so for people who are not physicists in the audience, when you see a physicist talk about dark energy, dark matter, what that dark means is that we don't know what it is.
We don't see it, we don't detect it. Yeah.
It's dark. Can't see it.
But to answer your question, the 10 or 26 dimensions, these extra dimensions, are somewhat separate to this idea of spooky action at a distance. They're not directly related. Maybe I could finally answer the question about how it is that we have these extra dimensions if you don't see them out the window. I don't know if people are interested in that story.
Yes.
But
yes, please.
Great.
Okay. So first of all, again, this is all speculation. I have to remind you that we don't know if any of this is true. But okay. So you look out the window, you see your 3 dimensions, and then the physicists, these crazy people that study this all the time, are saying maybe there's 10. So what does that mean? So it turns out that when you're talking about a dimension, let's imagine a 2-dimensional world, like, because it's easy. I've got it on the screen here. You can think of a 2-dimensional world. One way of thinking of it is just some big sheet that goes on forever. But what you could have instead of having a sheet that goes on forever, you could have a sheet that wraps around on itself, like the image on the right. Mm-hmm. Right. One of the dimensions could be curled up like this. So the way to think of it is, imagine a straw. Imagine you have some very long straw, right? From a long way away, that straw just looks one-dimensional, right? If you have a very long, thin straw and you look from long, it just looks one-dimensional. But if you zoom in and you look really close, at every point on the straw, really there's a ring there, right? And there are all these rings stacked up on each other. Right. So there's different ways of explaining where these other dimensions are. One of the ways of explaining it, it's not the only way, one of the ways of explaining it is that the 6 extra dimensions that we don't see, they happen to be compact. They happen to be, that's what physicists say. They say compact. These are compact extra dimensions that are small. Very small. The idea is that they're so small, it's like the straw. If you were an ant on the straw, you wouldn't be able to see, as the ant on the straw, you can see the the curvature. But if you're really big in comparison to the straw, then you wouldn't see this extra structure. And that's the idea here. You have these curved, warped up extra dimensions that, so at each point you can imagine on your 4-dimensional spacetime, every point has some additional internal geometric structure, which is like these wrapped up extra 6 dimensions. And you might think that this is kind of a crazy picture and this is making everything more complicated. But actually, this is, people would argue, one of the more beautiful aspects of string theory, because, or any theory of higher dimensions, because it turns out that if you didn't have these extra dimensions and you didn't have these wrapped up dimensions, these series would be incredibly boring. They'd just be empty space, more. It wouldn't be very interesting. This curled up structure actually gives you it accounts for the particles and forces that we see at low energies. So the idea is that the particular structure of the curled up dimensions gives you the particles and the forces that we see. Right. So to sort of explain
they're
that,
kind of necessary for the engine or the machinery of the cosmos.
yeah, in a way. So here I have sort of on the screen some pictures. The base, you can see these donuts and spheres, right? So in 2 dimensions, you can have spheres, you can have tori, you can have double tori, triple tori, and so on, n tori. So the particular way that the extra dimensions are curled up, their particular configuration will give your theory different structure, right? So the idea is that you can imagine the base of these pictures as being like the big 4-dimensional world that you see outside when you look out the window. And then you can imagine at every single point on that space-time, there's a wrapped up, curled up 6-dimensional structure. And the particular shape of that structure results in the particles and forces that we see. So that's the basic idea. Because if you look at these, if you imagine strings floating around on these extra dimensions, you could, over here on the left, you could have strings that wrap around the donut, right? You can't have those sort of modes on the sphere because you can't wrap around a donut on the sphere. So the idea is that you can get different modes and you can get these different vibrations in these different situations. And so one of the key things that people have looked at is how do you compactify, how do you collapse down these big dimensions into these wrapped up dimensions in order to go from a 10-dimensional theory to a 4-dimensional theory that has all the particles that we see when we do experiments. Mm-hmm. So that's one way of getting rid of the extra dimensions, and it happens to give us all the particles that we want.
Interesting. You wonder if you fly around the cosmos where they're parked, in a sense. Yeah. The fabric of everywhere or some sector. Go ahead, Paul.
I was just going to say, I should say that the visuals really help me better comprehend the conversation because it's pretty profound.
Yeah. What more do you have in your slideshow? Let's take a tour.
Well, not too much, actually. There's, I should say that this is actually also one of the problems with string theory, because people, when they wanted a theory that predicted everything that we saw. They wanted a theory that when you did this compactification, out would pop our world with all the particles and all the forces. That's not what happens. There are infinite possibilities of, there's huge numbers of possibilities. You can compactify in so many different ways and get different universes depending on the way that you do this compactification. So it could be that somewhere out there, outside of the visible universe, there could be some other sector of the universe that is compactified in a completely different way that has completely different physics. And then, so people talk about this landscape of possibilities. But so you wanted to see what else is in my slideshow. There's not too much. But there are some, I just wanted to point out that this is one way that you could get rid of the extra dimensions, but there are other ways. So you can look at, there's also brain world situations. So it could be that we have some 10-dimensional ambient space and we could just exist on a 4-dimensional sheet that's floating around in the 10-dimensional space. So there are these different pictures, and they all answer different questions. So this sort of brain world picture, one thing that people try to do is they try to explain why gravity is so weak in these pictures. So what people say is one sort of model that people build is they say that we could just live on some 4-dimensional sheet that's floating about in this 10-dimensional ambient space, like the surface of a bubble. You know, when you blow a bubble, the surface of the bubble is 2 dimensions, even though it exists in this 3-dimensional ambient space floating around. So the one nice thing that people talk about is in these scenarios, it might be the case that all the forces that we see, all the particles that we see, are sort of stuck to a 4-dimensional sheet, except for gravity. It could be the case that gravity could sort of leak off into the ambient space and spread out in the ambient space, and that's why people argue gravity might be so weak. But these are all really speculative models, and then it's not like these are accepted as being the reason that we see the world that we see. This is more giving you a flavor of some of the sort of the ideas that people are looking at.
How to account for these extra dimensions.
Mm.
Yeah. Yeah. Any others? Any other models?
Well, no, I have 1 or 2 slides about my own research a little bit.
Okay, let's hear about that.
But
of course.
Yeah.
So my research is, as I said, it's not string theory, but in my research, actually, I get 10-dimensional universes as well from a completely different direction, just by coincidence. I think I don't actually know why they're related, but so. Okay, so I told you I should stop my screen, by the way. Before I jump into this, I should look through the questions because people have been asking questions down the bottom. I want to make sure I'm actually answering some of them. Are there any questions that are unanswered? Does anyone?
We'll look at the questions, and people can raise their hands as well to ask a question. But I'd love to hear your research because we've been jumping around a lot, but I really want to hear what you're specifically finding and what you're discovering. And then I'm going to take the questions from the chat room as well, and I'll read through them and I'll ask them as well. So.
Okay, so I'll try to be quick because I think I can see that Dave Flegel has a question, but I'll try to be quick and then. But I'm not used to being in the guest position. I'm usually doing the interview. I'm usually the interview. It's hard for me to lose control of this. But anyway, so
good job.
So I told you before that when you're trying to build a physical theory, you have to make assumptions because otherwise, what are you doing, right? You need to make simplifying assumptions that allow you to do the calculations. So I told you, for example, that often when people are dealing with particles, they make the assumption that particles are just point particles. That simplifies things a lot. In string theory, you throw away that assumption and you look at strings. Okay, that's one direction you can go down. I make it different. So what I do is slightly different, but it ends up actually with some similarities. So it turns out that previously you mentioned Newtonian physics, general relativity, and quantum mechanics. So it turns out every time we discover a new type of physics, these big ideas, usually they're coupled with discoveries in geometry. So Newtonian physics, the geometry that you look at in Newtonian physics is sort of Euclidean geometry. You have straight lines and angles and, what you played around with in high school. If you want to travel at really high speeds, then you need special relativity. And the geometry that you're playing around with there is hyperbolic geometry. In quantum mechanics, just to give you some names, you have what's called symplectic geometry. General relativity, the theory of gravity, you want curved spacetimes. So there you need differential geometry. So, these dynamically, these geometries that have curvature that's dynamic. Okay, so the question I asked was the following, and this isn't just me. There's lots of other people working in this sort of an area. So I told you about in these string theories with higher dimensions, how these compactified theories where the extra dimensions are sort of curled up and wrapped up. So I ask a similar question. I asked the following question. If you have some 4-dimensional space-time, like what you see when you look out the window, and you wanted to add some geometry at each point. So each point in this 4-dimensional manifold, I add some additional structure, and that additional structure has to give me what we see in experiment. Then what does that geometry have to look like? So it's sort of
see.
like it's sort of backwards.
Reverse
So in string,
engineering. Yeah.
yeah. So in string theory, you assume that the geometry is all the same, like it's all curved normal geometry, but some of it's compact. And then you try to match the physics on the other end. I go the other direction. I say, this is the physics you want to get, and what does the geometry need to look like
To get there. Yeah.
to get there? And so at each point in space-time, I add some weird geometry. And it turns out that the geometries that I have to add at each point are very different to what you get in string theory. You can't really imagine them, you can't draw them, but they're mathematically well defined. There's a way of the equations make sense. Yeah, so they're internally consistent. You can't. I couldn't tell you what they look like. I have no idea, but they're mathematically they look very nice and they work. And so the interesting thing about that is, this branch of geometry, it's called spectral geometry or non-commutative geometry or non-associative geometry. There's sort of all these different names for similar things. And the interesting thing is, if you ask the question, what dimension? I told you earlier there are these different notions of dimension. If you ask in a very particular way, what dimension does this, what dimension does the internal geometry of the universe have to be? This wrapped up geometry have to be in order to match the particles that we see in experiment. What does it have to be? And the answer is that the internal space in the geometries that I play around with has to be 6. Right? So 4 plus 6 is 10. You get exactly the same dimension as you do in these string theories. And it's very bizarre. It comes from very different mathematics, very different logic. And I don't really know what the connection is. It's just by coincidence that very different directions, very different ideas give you the same dimension. And maybe it's deep, maybe it's a pattern, maybe it's just chance and we're both wrong.
What do you do in a day, and what are some of the projects that you work on? And do you meet with a staff and you go, here, I'm going to pitch this and I want to spend my time doing this, and then you report back like a normal business? Or how does it flow for you?
And where do you see yourself going?
Yeah, good question. Yeah.
So this is you want the authentic scientist. This is like what my podcast aims for. So if I don't do a good job at answering this, then I'm just rubbish. Okay. So what do I do? So I can tell you about the project that the paper I'm currently working on. This is actually very hard to explain without using any math, but okay. So in the models that I build, what happens is there are very particular types of particles that you need to have in the model in order to match reality. You need to have what are called Weyl fermions and Majorana fermions. You need these Majorana and Weyl conditions to be imposed on your matter particles, right? So for anyone who doesn't know what those words are, you need certain types of particles. And it turns out that asking that these types of particles are in the model imposes sort of certain restrictions on the shape that the geometry can take.
Okay.
And it turns out that this is I'm trying to do this with no equations, and it is quite.
It's
But if you can't explain your own research, you don't know it well enough. So I'm risking this. But essentially what happens is, in the usual way that people play around with I'll tell you the actual words, and then I'll try to flesh it out. What people usually try to do is there's this property called associativity. So most mathematical objects have associative structure. What that means is if you take two numbers and you multiply them together, and then you multiply a third, it doesn't matter where you put the brackets in any expression.
Okay.
Okay. So in all of the geometries that we play with, you have what are called coordinate functions. What's a coordinate function? A coordinate function is just a set of numbers that you assign to a point. So if you imagine in the room that you're sitting in, if I wanted to label a point, this point up here, I could say it's 1 meter from the floor, 2 meters from the wall, and 3. So I can label, I could label this point 1, 2, 3, right? And I move over a little bit and I get slightly different numbers. So I have some coordinate functions or labels, number labels that I
to describe the relationships between the parts.
Right. Now, these numbers, at any point, you can add them together, you can multiply them, and usually these numbers associate. So it doesn't, like in any of the mathematical expressions, it doesn't matter where you put the brackets.
Gotcha.
It turns out, in order to get the particle content that I want in the models, I have to throw away this associativity property. Now my coordinate functions are something more complicated than just numbers. There's some other objects with some more structure locally, and that structure accounts for all the particles, but it no longer associates. And all your usual ideas in geometry break down when you throw away this associativity property. So you can no longer talk about vectors. You can no longer talk about all the usual geometric objects like area and all these things. You have to ask, what do these ideas mean if you throw away these properties? So this is what I've been doing. I'm trying to build a geometry which recreates all the particle content that we want in our standard model of physics. It turns out I've been forced, just like in string theory, you're forced to work in 10 dimensions. Here, I'm forced to throw away associativity. And yeah, so now I have to work out the mathematics of what that means. I have to redefine what area is. I have to redefine everything in a consistent way so that the geometry makes sense. And that's what I'm doing. So that's the current paper I'm working on.
Are you doing this in a computer, running it? Are you on one of those giant blackboards like in the films? And, you're writing down these long equations.
From the
What does this mean? Do you go to bed at night thinking
Dreaming
about this? Do you wake up with a eureka moment? Do you run different scenarios? You're plugging different things in?
It's funny.
Yeah.
It's funny you ask about the eureka moment because I have many times in my life woken up in the morning after I've been up all night, like thinking about some complex calculation, and almost 100% of the time it's wrong. Like whenever I have the dream that this eureka moment and I wake up in the morning and I try to write it down, it's almost always complete garbage. It turns out that sleeping Shane is terrible at physics, unfortunately.
What do you talk about at cocktail parties or at the dinner table?
Well, when your family calls you and asks you, what are you up to? How are you doing?
Who can you talk about this stuff with?
Do you really want to know?
Because what I'm concluding
that's why he has
is
a science podcast. That other people can follow his conversations with him. And
But this stuff is interesting stuff to talk about, just to get your brain confused. That's a delicious feeling too, right? We like order, but we like novelty. Right? We like to stretch. We like to go, the universe is a much more mysterious place than we know. Right? I stick with, we know 5% of it. The rest of it is just a big mystery. Wow.
And when the majority of the population is concerned with cats on social media and YouTube rather than paying attention to quantum physics.
Well, there's Schrodinger's cat, isn't there? So comments from the, we've a little bit of time left.
Well, there isn't a lot in the chat room other than we've already gone through it. But Bob made the comment physics when we were talking about consciousness. Bob said physics doesn't apply to consciousness; it applies to matter, energy, and motion, etc. We could get into that discussion.
Okay, but we have Max Planck saying.
Yeah, I know. So
I regard matter as derivative of consciousness.
Yeah.
I regard consciousness as fundamental.
Right.
Everything that we talk about, everything that we regard as existing postulates consciousness. Right. Where is that in part of the equation? Has anybody input, quote, consciousness? You can't reduce it to a mathematical formula, mind you. Yeah. But shouldn't it be part of the equations here?
Well, I can tell you where I think it comes from.
Okay.
If I had to guess.
Okay.
I think it's emergent phenomena. So I think I think consciousness comes from it's like an emergent property that comes from our very complicated brains.
Just us or all of life, right?
So I think,
yeah.
so I think to answer your question, I think probably you won't find like a fundamental equation like you would for a string or a particle or a force, but rather I imagine it'll come from collective phenomena. And that kind of makes sense because, you know, the creatures that we know that have consciousness usually have quite complicated brains with many neurons that all interact in complicated ways. And that's also how we build artificial intelligence as well, right? We have these neural networks with huge numbers of neurons. So I imagine, I imagine at the level of the equations, it's probably not going to come out from, you know, you're probably not going to have an E equals MC square equation. It's going to be something, in some sense, nicer as well. I like the idea that consciousness sort of derives from this collective behavior. That would be my guess. So Bert's got a...
Yeah, one of the questions that I kind of asked and just went by is that as I was talking about Wheeler, the great physicist, talking about information in some fashion being more fundamental than space-time. And I think loop quantum gravity sort of plays around with this, but I would put it to you like this. If what's going on in our brains is this boiling mass of information, and if there is some physical connection to information being the substrate of the universe, perhaps that is a possible way in which you might build a bridge between consciousness and physics.
Yeah.
So, go ahead. I just want to say, Carolyn, you said this has been your most interesting physics lessons ever. Thank you. I know Shane would want to hear that, so pipe up. And then, are you saying brains generate consciousness, or perhaps our brains, just like so much of us, is tuned to download consciousness? I mean, you could argue either way on that. You could, and where does spooky affected distance come in? Because we can kind of see that at play in everyday life. Yeah, I know, beyond your wheelhouse. You got to answer Bert.
It's beyond my wheelhouse.
I want Carolyn to say thank you, among others, because this has been fun. This has been fun just to contemplate that, wow, this universe is really mysterious and interesting, right? And you guys are working on some cool stuff. You've got the best jobs ever to theorize this. I know it's hard work, but wow, you're spinning out these interesting possibilities and answers, and you really have nothing underneath you, right? Not much underneath you to support this, but a lot of, yeah. Go ahead.
There's a lot of people underneath.
Yeah, that's what I was about to say. A lot of thinkers and shoulders that you're standing on. Yeah. Wanted to acknowledge them. Max-Planck amongst them, among many. Yeah, Einstein, Newton, the rest of them. So.
But no, to answer your question, I would say, I mean, if I had to guess, I'd say brains generate consciousness. And there's like a,
I would argue the opposite. I would say that we have the apparatus, the sensory apparatus to download, to put our finger into the socket of the cosmos, that it's a matrix and we get to play in it. And just like everything else that we have of our sensory apparatus, it's about tuning to it, detecting it, playing with it, downloading it. Both. So you could argue both. Yeah. But I'm not a theoretical physicist, but that's not the only domain that gets to answer these questions.
No, but as I said, I'm not an expert in this area. But I think that the reason why I like this image is because then you can start asking questions about, maybe you can in your framework as well, but I like being able to ask questions like, well, it could be, here's an image that people talk about. It could be that beehives are conscious. Right? You have this collective behavior from a group of bees that together do some really complicated behavior that the individual bee can't do. Right. And so there you've got this, good analogy. You know, the magic is in here in the actual system that's there. It's like you don't necessarily have to look outside for the magic. It's really there in the collective behavior of these bees. And you can look
organisms.
or you can look at you know, there's all this richness when it comes to consciousness. Like we're now at a stage where people are building what you might argue as consciousnesses, I can't say the word, in the form of artificial intelligence, right? So we're building these things now, and we're building them from collective behavior, and we're going to have this really broad and rich sort of tapestry of different notions of what consciousness is. And I think this view of seeing things from this collective phenomena, it gives you access to these different.
And it's probably maybe it's not mutually exclusive. Maybe it's all of the above, right?
It could be that this is just different ways of accessing the consciousness that you're talking about.
And
as well.
how do atoms come together and create life? I mean, we're back to these fundamental questions, and they're fun to jazz on. So, Bert, thank you for co-hosting. I so appreciate this because you've read all this stuff. Yeah, I'm the watching the PBS specials on the science. You've read the books. Thank you. So, your thoughts, Bert?
Well, I did have a question, and it does, I guess, overlap somewhat with the questions that we've been discussing. But with respect to the holographic cosmological theory, their big argument coming from Stephen Hawking's about the loss or the preservation of information falling into a black hole. And it's gone around and around, and we talk about black holes evaporating and so on. This is the problem that I have, is I've been reading this stuff, but I'm not clear on exactly what kind of information they talk about when they talk about conservation of information. Now, anything falling into a black hole, one of the theories is totally ripped apart. So the information they're talking about cannot have anything to do with any pattern that we perceive in our world around us. It's not an aggregation of matter. It has to be at the particle level. So do you have any insight into exactly what pieces of information that they're discussing when they're saying it falls in, it disappears, or it doesn't disappear? But what are they talking about? What information?
Yeah, so this is actually a really complicated topic that, again, is outside my wheelhouse. So I can give you a cartoon, but I'm going to look silly if I try to dig deeper than the cartoon, but I'll give you the cartoon. So the idea is the following. If you look at the equations which describe a black hole, the equations describe the black hole as having no structure. It's just you've got a horizon that has nothing. It's just empty space-time, with no structure at all. And so the question is, if I throw I throw a teapot or something into the black hole, there's all the information that is held up in the configuration of that teapot. If I throw that in the black hole, then the black hole gets a bit more mass and grows a little bit. But I could have thrown in some other object, your kitten or a hat or something. I could have thrown a different object into the black hole of the same mass, and then the black hole it only has one parameter, it just has mass, which describes it, or maybe angular momentum or charge, but very few parameters. And so in these two scenarios, I start off with a cat or a hat or a teapot, or a cat in the hat, and I throw them into the black hole. So my initial state was very different, but my final state is the same, like two black holes of a slightly larger mass. Yeah. And the question is, where did that information go? Like where is the information being held? And so that's the big question that people are currently arguing with. And the idea is that people talk about this idea of quantum states being held on the surface of the black hole on the horizon.
Is that a Planck tessellation? Is that basically a Planck length tessellation?
Yeah, that's the idea, that you have like these little Planck area units, And actually, this is again not my area, but string theory, again, not my area, not a calculation I've looked at. Apparently, you can actually calculate these microstates in a sensible way in that framework, and you get the right answer. But anyway, it's completely outside of my wheelhouse.
What I want to say is thank you, Bert, and thank you, Shane. It has been fun to dive into the deep end of the pool and not drown. So you've been a good guest, keeping us afloat and not adrift here. It's really fun to just try to grapple. I mean, you wonder, what do theoreticists do? How do they talk about this? It's just fascinating. Right. And I wish more would be done even in children's books, right? Because A Wrinkle in Time, I have to tell you, every kid I know, A Wrinkle in Time, with the tesseract, and you bring the space-time together like this, and then you can just flip I mean, those are galvanizing and exciting ideas that stay with us. And I think there needs to be more of this made accessible to us in the general public out there, because we are supporting this is our tax dollars at work globally, to push the seams of the envelope in this way. And I know it's difficult to talk about and wrap your head around. Thank you. You've done a great job. I appreciate all the work that you put into your slideshows. I appreciate the work that you and all your colleagues around the world do, and the Bob Woodruffs and the Tony Hulls and the Sherilyn Morrows and all of you out there doing this and speaking to us and kind of dazzling us with these extra dimensions, and I can say that in a literary way, of really trying to grapple with what we're made of, who we are, our place in the universe, these eternal questions. And I want to also quote the founder of our institute, Dr. Felicitas Goodman, anthropologist. And she said, humankind has been grappling with these questions of the nature of reality for many, many, many thousands of years, and no one has come yet to a satisfactory answer. And so the quest continues. These are the eternal questions for a reason. The mysteries are mysteries for a reason. And this is such a magical universe. It's so broad, it's so deep, it's so mysterious. It's a cool place to hang out and live. Wouldn't you rather have it this way, being undecipherable? The eternal quest will keep us going for an eternity. Right? And so I just want to applaud you and all the physicists out there and all your efforts at this. And what a fun day job, I have to say, to sit around your conference room and grapple with these things. And I know it's like a secret guild, right? You understand these terms, and we can only get an inkling of it. And so you really need to be in the cognoscenti to speak about this at depth. But I appreciate the effort to come out and alert the rest of us as to what goes on in these various trenches. And really, as a generalist, that's my joy, is to understand and get a glimpse, not to understand, because that would imply going down to the bottom of the trench, but to see the trenches out there at work and to appreciate the diversity of thought, of query, of journeys, of quests, of answers being sought in these various fields. It's just delightful. It's like a sense of a peaceable kingdom, right? All these bees buzzing at work in their various flowers and gathering the pollen. And what you put it together into this beautiful matrix of human endeavor and understanding. And I think all of the above, I'm an inclusivist, like all of the above is important. I understand, Bob Woodruff, that you're saying that we can only talk about quantum mechanics as the material world, but no, all of us can engage in this way and at least ask questions, right?
Well,
thank you. It's been a delight. Go ahead, Bob. Open up your mic. I quoted you. Yeah.
I think we can ask questions, but the Schrödinger equation does not have a variable called consciousness.
Well, okay, but we can explore consciousness in these other ways. Yeah. Well, and I appreciate this. I also want to give a shout out to Bert. Bert, you've been a friend of ours for decades. He was a frequent guest on our radio show. Bert was the guy that I could always call up in an emergency and pose a question, and he would have a reasonable and well thought out answer. Yeah. So I appreciate these guys in our life and the walking filing cabinets that you are. And so, and it's
And
been
as
fun
Shane-
to dance. It's
Go
been
ahead.
fun to dance in this arena. I don't know the steps, but it's been fun to dance. Go ahead.
Well, as Shane said, it's not my area of research. And trust me, this entire conversation is not my area of research. But
No, no, no.
that's-
But I
that's
live in
why
the
we-
universe, so
But
you know,
that's why we call
have
it
a state.
conversation for exploration. We're trying to
Yeah.
explore ideas that are outside of our known areas, and
That's how you stretch yourself, right?
that's how you make these connections.
Yeah, we're all stakeholders in the universe, so we
Right.
all want to compare notes on the journey, right? This is what it's about in our
So,
various endeavors.
Thank you so much, Shane, for
I really appreciate it. Thank you so much for inviting me and for listening. It's really quite an honor and a privilege to have people who want to listen to what you have to say. So thank you, Bert, Bob, Dave, Julie, Marilyn, and everyone else whose names I can't see on the screen at the moment. But thank you for listening along. And it's a pleasure. So thank you very much for inviting me. Am I allowed to do one last plug or?
Sure,
please
yeah.
do.
Oh, I'll do the plug first.
For
Look,
Escaped Sapiens, yeah.
yeah. If anyone wants to help me build up, because I'm trying to build this platform which makes this authentic, or gives this authentic view of what science is, where I interview all these different scientists. So please, if you're interested and you think it's something that you think might be valuable or interesting, check it out. You might like it. It's called the Escaped Sapiens.
We want to thank everybody for joining us, and also please everybody take a moment to also thank Shane for taking his time to do this and bring us on this amazing journey.
Thank you.
Yeah, we can suggest a few scientists for you too that should be
Thank
interviewed
you.
by you.
Thank you. Thank you.
Yeah.
Thank you.
Yeah.
Woo.
All right, everyone. Thank you
Thanks,
so
Shane.
much, and thank you, Shane.
All right, it's been a pleasure,
Really
everyone.
fun to kind of see, get a glimpse into your world.
Yeah.
That has been very instructive for us. Yeah.
Thank you.